everyone, I'm Wenhao Li from Shanghai Jiao University. The paper I'm going to present is called AdAttester Secure Online Mobile Advertisement Attestation using TrustZone. This work is done with my colleagues Haibo Li, Haibo Chen, and Yubin Xia. Firstly, let's take a look at today's mobile ad ecosystem. This picture shows the 4 different parties in the ecosystem: the application developer, the mobile advertiser, the mobile user, and the application market. To embed the ads inside an application, the application developer first registers and gets ad plugin from the mobile advertiser and includes this ad plugin in her application, and then publishes the application to the application market. After the user downloads and opens the app, the application library is responsible. The ad library, is responsible for fetching, displaying, and handling ads. After a user sees or clicks an ad request containing the ad impression or click information will be sent to the mobile advertiser. And the mobile advertiser will pay for this ad action according to this ad request. Typical ad events are charged by ad impressions or user clicks. Currently, mobile ad occupies large marketplaces and is one of the major pillars for application developers. However, this huge revenue ecosystem is now severely threatened by ad fraud, where roach code trick ad providers with fake ad impressions or user clicks. And some survey predicts that about $1 billion lost due to ad fraud in 2013. So generally speaking, there are 2 kinds of ad frauds. The first is called boot-driven frauds, that using boot network to forge ad impressions or user clicks. And the second category is called interaction-driven fraud, based on the user interaction, including the placement fraud and the unintentional request fraud. The placement fraud is placing the ads in violation of ad guidelines so as to receive ad impression fees without affecting user experience. And the unintentional request fraud is to send ad request without user's awareness. So an ad request may be sent from a real user, a real device, or from a boot network, or even malware. And the ad server needs to distinguish whether the ad request is sent by a user instead of a boot, and his ads are displayed on the user's screen without violating his policies. However, due to the lack of proofs to the remote server, it is hard for the ad server to distinguish between legal ad requests and illegal ones. So there are some existing techniques on recognizing user requests. The first technique is using CAPTCHA, but since it needs the user involvement, it is hard to use, especially in the ad ecosystem. And the second technique is using TDM and heuristic method to sound user clicks. But this is not accurate, and this technology is not available in the mobile device. And the most common approach is using big data inference and heuristic methods. But this method has high false positive and false negative. So our goal is to provide assurance to the ad server that an ad request is issued by a user instead of a boot. And an ad is displayed on the user screen timely and intact. So to make our system practical, 4 properties are desirable, including the non-intrusiveness, incremental deployable to the existing ad ecosystem, privacy preserving, and with a small TCB. So the key insight of our system as a tester is to provide trusted proofs to the remote server using mobile trusted hardware. So the fundamental question is, what kind of proofs we need to collect and send to the ad server? As the primary means for an ad server to determine how much to pay an ad application developer is through counting the times of ad impressions and user clicks. AdAttester provides 2 security primitives that serve as a basic building blocks to build a secure online advertisement system. The first security primitive is called unforgeable clicks. That a user action could not be forged by malicious code. that send ad requests in the background without users' awareness. And if such situation happens, the ad provider could easily detect. And the second primitive is called reliable display. That's if the content of the ad is displayed on the user screen, a verification proof of the displayed content and the duration it displays on the screen will be generated and sent to the ad server for verification. So here shows how AdAttester works. We have a mobile device and an ad server. When the user sees or clicks the ads inside the application, the field element of the click or field area and its eigenvalue will be calculated and signed using the device key. And this information from the attested message will be sent to the ad server for verification. And the ad server will verify whether the attested request is valid. So the challenge problem is how to keep the integrity of the generated data and the proof data. So we use the trusted hardware TrustZone to guarantee the integrity of the data. ARM TrustZone is a security feature of ARM processors and is now widely available in mobile devices. TrustZone provides two separated worlds, normal world and secure world. The secure world is more privileged and accesses all states of normal world, but not vice versa. The memory region and the peripherals could be assigned to secure world accessible only or by both. So, considering the threat model, we assume the hardware is trusted and the small software stack running in the secure world is trusted. We assume the hardware is equipped with TrustZone and the persistent per-device key pair, and this is now available in our devices now. And for the stakeholders, we assume the ad provider is benign, and her ad server will not be compromised. This figure shows the architecture of AdAttester. In today's mobile systems, a rich OS such as Android runs in the normal world, while a small secure OS runs in the secure world. The secure OS only does some secure sensitive tasks on demand, and all other tasks are done in the rich OS. In AdAttester, we add an AdAttester service in the rich OS to provide attestation APIs to applications with ad library. To securely track and attest ad information, we have a secure application called AdAttester in the secure world to attest the ad request. For applications with ad library, they could use our attestation API and send the ad request to the ad server for verification. Internally, to securely obtain ad click and display information, we set the display, controller, and the touchpad device as secure devices. So they only the secure OS will operate them. And the device drivers of the tool is implemented in the secure OS too. So this figure shows the ad flow tracking framework. The first phase is the offline feature extraction, which takes a list of ad images or videos as input source, and spreads these images or videos into a list of ad images and calculate the eigenvalue of these ad images. These eigenvalues, together with the ad information, will be stored in the feature repository. After a user clicks or views an ad, the attested ad request will be sent to the ad server. The ad server will check whether the ad request is attested. If true, we will further test whether the ad request comes from a TrustZone enabled device and verify whether the eigenvalue of the ad from the ad request matches those valid ones in the feature repository within a predefined deviation. For the ad request that's not attested, we just use the legacy fraud detection system to detect fraud behaviors. Considering the deployability of AdAttester, the mobile vendor needs to use our patched OS firmware into their device, and as well as the device keys. For ad providers, they need to modify their ad SDK to use our attestation service. For mobile users, they just need to install a small attestation application in the secure OS of their device. So while the usefulness of AdAttester depends on whether it could be largely deployed in mobile devices, the design of AdAttester could also motivate some other innovative scenarios which could bring benefits to both mobile users and service providers. For example, the content providers could pay for the traffic generated by mobile users watching their promotions or ads, and AdAttester could provide such proofs to content providers. Besides, the AdAttester could also attest ads to the application developers. So we implement AdAttester in the real hardware, and the OS running in the secure world is T6, which we built from scratch. And the rich OS running in the normal world is Android ice cream sandwich. To calculate the eigenvalue of the ad image, we use the perceptual hash scale persistent algorithm, which generates a 64-bit hash for an ad image. So one problem is the display controller driver code is very large and complicated. Directly porting the driver code to secure OS would enlarge the TCB. Since we only need to know the exact location of the frame buffer, the secure world only controls the device register access, so that most of the driver code could be kept unchanged. And these two figures shows the detail. An access to a device is changed to a crossable core. This design, the overhead of this design is very small because almost all the updates are read after the device driver is initialized. Considering the implementation complexity, the TCP size is less than 7,400 lines of code, and the normal board OS modification is quite independent, and thus could be easily ported to other versions, other OS versions. So to evaluate the effectiveness of AdAttester, we use the AdFlow dataset from AdFlow and select 183 applications which have typical AdFlow behaviors. We firstly modify them to use our AdAttester API through repackaging, and then compare the results with our manual exploration. We totally instrument 26 ad libraries, and for each ad library, it takes about half a day for a person to instrument. In our results, we found that AdAttester could detect all of the flaws we found in our manual exploration. For boot-driven flaws, since the ad request is not attesting, and thus could be easily recognized by the ad server. For the performance impact, we evaluate the ad view tracking overhead using AnTuTu benchmark. The left figure shows that the overhead is less than 0.6%, and for the input event handle latency, the overhead is negligible. And we also evaluate the ad network traffic increase. The overhead later is less than 3.3%. We also evaluate the ad server response latency by simulating 100 to 1500 concurrent user requests using Apache benchmark. And the average latency increase is 0.04 milliseconds. And the right column, the right table shows the duration for getting an attestation block in a mobile device. Since this latency is sensitive, we used in asynchronous notification to mitigate such latency. So to conclude now my talk, we observed that the lack of very reliable attestation proofs is the key obstacle to defend against mobile ad frauds. To this end, we propose AdAttester to effectively detects and prevents all well-known ad frauds by enabling two security primitives, namely verifiable display and unforgeable clicks. We have conducted a full implementation in the real hardware and a comprehensive evaluation showing the effectiveness of AdAttester. So this is my talk. I would like to take any questions. Thanks.